Okay, so we continue with our next speaker, Benjamin Montesinos, and he will talk about the circumstellar material around main sequence stars looking for exocomets and related phenomena.
Okay, thank you very much for the organizers for inviting me. And and probably the first question to be answered is what I'm doing here, talking about exocomets. When Professor Green invited me, I wrote him a message saying, okay, I've worked on this kind of stars a few years ago, but in the last few years I've deviated to other topics. And then I put here a paper where you can find the answer to my question, but he wrote me a message that I read literally. Many years ago, I supposed that the redshifted absorption components, which we observe in the sodium-1 lines in spectra Uxors, have a similar origin as those in beta peak. Later, however, we have shown together with Antonella Nata that such a spectroscopic activity can be also explained in the framework of magnetospheric accretion, and this explanation dominates at present time. The intensive accretion process masks the spectroscopic signature of grazing exocomets, and only in the late phases of PMS evolution in stars with debris disks, the comet-like activity can be observed. So as you can show in your talk, the very important component of circumstellar activity which exists in young stars as a sequence of planet formation process. So what we are going to talk about here is the next phase following the evolution of the stars that we've been discussing here this week. Just another quote that I found in a recent paper talking about Arset Piscium. I think that the last talk of this workshop is about this star. And then there is a quote saying, well, explaining the potential origin of this variable absorptions in the circumstellar lines, and then the quote says, for A-type stars, these features are generally interpreted as sun-grazing exocomets, and the same may apply to Uxors and these Arset Piscium. So this is more or less the link between the topic of this conference and the exocometary world. So a couple of slides with nice images to remind you that in the early phases of stellar evolution, when the star is visible, we have a protoplanetary disk, which is made of gas and dust, surrounding stars with ages of a few mega years. This is an ALMA image of the very famous TW Hydrae, a 10 mega year old star. And this is the central part of the disk with this cavity, which has a radius more or less of 1 AU. Then we have the debris disk. This is the also very famous debris disk around Fomalhaut, a star which is 440 mega years old. And these disks are made mostly of dust and debris surrounding more mature stars. And the gas from protoplanetary disk has been depleted, either because accretion or photoevaporation or formation of planets, and the dust has been replenished by collision of planetesimals. Then in these two phases, we know that planets are formed, but also other things are formed in the exoplanetary systems. And then we have, of course, planets, we have planetesimals, we can have asteroids, we can have belts, dust, a lot of things. And whereas exoplanets are now routinely detected, and we know more than 4,000 exoplanets already confirmed, we have very little information about small bodies that, of course, are important to understand the architecture and the formation of planetary systems. The other two were images. We don't have images of exocomets. This is obviously an artist's impression. Okay, we have indirect evidence of the presence of small bodies. For example, if we observe in the near or far infrared the stellar energy distribution of stars, this is a CD of Eta Corvi. Eta Corvi is an F star, and actually I will mention it afterwards because it's the only F star for which exocomets have been found. exocomets or exocometary-like events have been found only around A-type stars. So you see here the photosphere. These are optical photometry, and we have here Herschel observations. This figure comes from a project, a key project carried out with the ESA satellite Herschel, which was coordinated from Madrid, led by Professor Carlos Eiroa. The acronym is DUST, around nearby stars. And then you can see here, this would be the photospheric SED, and we have here two humps denoting the presence of warm gas at 300 Kelvin and cold gas at 40 Kelvin. But one interesting feature of debris disks is that we find also gas, and we see two kind of features. We see molecular lines in emission. This is a carbon monoxide line in the HD 181327. And this implies the presence of a cold gas at temperatures around 50 Kelvin. And we also see metallic lines from refractory elements like magnesium, calcium, iron in absorption, and that implies the presence of a warm or hot gas around the star in the debris disk with temperatures of around 1000 or 2000 Kelvin. Here you can see the iron 1 circumstellar lines in the very famous Beta Pictory stars. And then the question is, what's the origin of this gas in the debris disk where the primordial gas is supposed to be depleted? So we can have two answers. Primary is that the gas is a remnant from the protoplanetary disks, and there is a paper by Agnes Kospal showing that, or the origin can be secondary, coming from the evaporation of icy bodies, colliding comets, or planetesimal or grain-grain collisions. And probably we have a mixture of both things in real life. The most conspicuous circumstellar features, which are easy to observe in A or B-type stars, but are much more difficult in later types because the spectra are much more complicated, are the narrow features superimposed on the calcium 2H and K lines and in the sodium 1 doublet. Which we are seeing here, again, is in beta peak, the residual intensities after subtracting the very broad calcium 2 profile here and the sodium 1 profile. Just to remind you the architecture of beta peak and the properties is a A65 star, is fairly young, 23 megayears. This is the IRAS discovery image of the debris disk around beta peak back in the mid-80s. And then you see here the disk, which is slightly warped. And you know that there is a planet that was discovered by direct imaging at a distance of 12 astronomical units. Well, this is a figure taken from a quite historical paper, because here you have the calcium 2K profile in beta peak and observations taken in 84, 85, 86, covering a couple of years. Then you see here a stable component at the radial velocity of the star. This stable component comes from the disk itself, but then you have here a huge variability in the red. So these features are usually called red absorption components. And here we come to the hypothesis of the origin of these red absorption components. How can we detect an exocomet? Imagine that you have a comet that is approaching the sun in this case, or the star, and then we have two tails, the dust tail and the gas tail, because as the comet is approaching the star, the ice is sublimating, and then the nucleus is outgassing, and then we can detect the traces of that gas by spectroscopy. We are lucky and the comet is crossing our line of sight. And the dust tail can leave some photometric traces. I'm going to concentrate in the spectroscopy side of the detection. So what's the explanation of these red absorption components? So imagine you have here the star, you have a comet that is coming here, the comet is sublimating, and this is for the case of beta peak. So you have here the stable component, and this transient component comes from the gas that is coming from the sublimating ice. So we are identifying the observational fact of red absorption component, RACs, with falling evaporating bodies. That's the hypothesis. So if we assume that this hypothesis is correct, this figure that I showed you before was the first report of exocomet in a star back in the 80s. And then there is a more recent paper 5 years ago by Kiefer et al., where they collected a lot of observation. I think that they analyzed, well, this star has been observed thousands of times, and they identified two families of exocomets, some with very narrow circumstellar absorption profiles, because they claim that it's a family of comets which are exhausted and they have little material, whereas this big absorption comes from a family of comets that has been probably destroyed colliding with a variety of radial velocities. And they even identify here some blue absorption components, and they also claim that they are exocomets. So what we did, and we planned in the last 3 years, is a big survey trying to detect exocomets in a variety of stars. So we selected 117 objects. Beta peak is not in the sample because beta peak is very well known. And then you see that the survey is very inhomogeneous and biased, because we had put in the survey stars with debris disks, stars belonging to Jan association, stars where these red absorption components had been already observed, stars with near-infrared excesses, stars with hot gas, so classical shell stars, stars where this cold gas has been detected, and some lambda Boo stars. You know that these are stars with some abundance anomalies. They have solar abundances of carbon, nitrogen, oxygen, and sulfur, but then they are depleted in, for example, iron peak elements by a factor of 100 with respect to the sun. So our aim was to monitor the possible occurrence of FFs in stars where this phenomena had been already observed, and detect these red absorption components or FEBs in the other stars. So we took something like, more than 2,000 high-resolution spectra during more than 2 years of observations using these 4 telescopes. And to our knowledge, this is the largest survey ever made looking in a more or less systematic way for exocomets. So some results from the survey. So, of course, we observed each star several times and then built time series and detected things like that. When you take the median spectra of several campaigns, and then we attribute this to FEBs. I have to say that if you compare our detections with what you observe in beta peak, for example, there are orders of magnitudes in the intensity of the variability. There is only one star that I'm going to show you afterwards that shows very wild variability, but we don't know if this can be attributed to exocomets. We also detect narrow stable components in quite a few stars, both in calcium and in sodium. This is more or less a result of our survey. Out of the 117 stars, we don't find any gas evidence in 55. We find some circumstellar gas of unclear origin around 9, but we are not sure if that comes from the interstellar medium, because it's sometimes in A-type stars that have very broad lines, it's very difficult to estimate the radial velocity. And probably the important result of the survey concerning exocomets is that we find variability in these red absorption components in 18 stars, so it's more or less 10% of the sample. So in the previously known stars with FEVs, we detected again variability in 12. We didn't detect anything in 8 of them, and we discovered 6, we added 6 more stars to the census of stars with exocomets. So these results, which are, by the way, the nucleus of the thesis of our student Isabel Ribollido, that she will defend thesis in the fall. So we have 26 stars, all of them A-type, but this one, which is Eta Corvi, show variability in circumstellar features, which we interpret in principle as falling evaporating bodies like scenarios. Another interesting result is the following. This result corresponds to 18 debris disks with, where cold gas had been detected. And here, I've written the inclination of the disks. And what we find is that in 8 out of 9 edge-on inclinations, we have traces of warm gas. Whereas in 7 out of 8 more or less face-on disks, they do not show absorption. So we think that this is a geometrical effect, in the sense that if you have a disk with a low inclination and you don't detect warm gas, that doesn't mean that this gas is there, and it's because it's a geometrical effect. If the disk was more edge-on, most probably you would detect this hot gas around. This is the wild star that I told you about before. It's Phileo. It's much older than Beta Peak. It's 500 to 900 mega years, another A-type star. And then, I don't know if you can read from the back of the room, these are observations taken in March 2016, 26 and 29, during three nights. These are the K and H residual profiles, so the photospheric line has been subtracted, and then you see here huge variations in the line profile. We don't know if we don't know the origin. You see this in many other lines. For example, you go to the infrared triplet and then you see these variations. Well, we leave this here. We have many observations. You see in other campaigns these huge variations. So we keep working on star because it's quite interesting. And then a warning, if at some point you are studying variability in these red absorption components, because in some occasions, the variability which is attributed to falling evaporating bodies might have another origin, which is much more simple to explain. And the example, this is a work that we published very recently, is the star HR10. HR10 is quite famous. It's a bright star. V magnitude is 6.23. And before our work, it was treated as a single object. In the literature, the spectral type assigned is A254. a large V sin I, and an effective temperature around 9,000 Kelvin. And the interpretation of variability in the circumstellar components, mainly in calcium, in all the papers published in the mid-80s, was always attributed to falling evaporating bodies. So when we started studying this star, we followed that approximation. And for example, these are observations taken from the archive, from the VLT archive. This is the K profile and the titanium-2 profile, both of them in the blue. In black, you see the residual circumstellar line, and then the decomposition in Gaussians in red. And then look at the behavior between June 28 and July 27. So you see here this component moving, and this here you are unable to see any component, but there is here a small component appearing, and then you plot in other lines the red components and the blue components moving. So we say, hey, this is very interesting. We are spotting an falling evaporating body-like event. But then we started collecting our own observations and archival observations, and then you see this is the photospheric profile, okay? HARPS January 2015 and HARPS December 2017. In this rectangle, we zoom the circumstellar components, and then you see here, this is the spectrum, and then you see here a deep component and a shallow component. And about 3 years later, they are swapped around, and then you see that the deep component is here, and the shallow component is here. At that time, we received a message from some colleagues that were observing with a Pioneer sample of stars, and they said, we have some hints that HR10 can be a binary. So what we did was to first put a lot of proposals to take our own observations and do fine monitoring of the star, and also go back in time and collect, well, any spectra published since this star was being studied. So you see here, we have 32 years of observations, and these are the radial velocities measured of the two deep and shallow components, okay? This observation corresponds to our campaign, so you see these are quite well populated, and here we have some observations. A very simple periodogram analysis showed that, I don't know if you can see in pale red and blue, that you can accommodate these sinusoidal curves to the observations, and a deeper and more exact analysis shows that actually the star is a binary. You have here the Pioneer images, and the interesting point of this star is that we are measuring the radial velocity of each circumstellar component, and this circumstellar component, each one are tracing the radial velocity of each star in the binary. Okay, so the result of this is that this is the first detection of a main sequence binary with individual envelopes around each component. There is no traces of circumbinary disk. The configuration, the inclination is more or less 85 degrees. This is more or less what you see. Each star has its own individual envelope, and the closest approach, because the period of the binary is 750 days, it's only 2.39 AUs. So it's a very interesting system. So what is the message? That if you want to be certain that what you are seeing when looking at one of these stars are really exocomets or falling evaporating body-like phenomena, you have to collect observations over long time spans to rule out the possibility of misinterpreting the origin of the variability. Actually, from our survey, we have now two more candidates, two more stars, whose variability has been interpreted as FEVs, and that seems to be binaries. So these are the take-home messages. At the top, I wrote again the result of our survey. Here I leave the name of this star if you are interested. We have all the spectra. If you want, we can share the spectra with you. We have this interesting hot-cold gas relation. The inclination angle favors detection of closing gas. And then this first example of variability in circumstellar components not due to exocomets, with the interesting fact that we have two individual stars with two individual envelopes and no circumbinary disk. Thank you very much.
Thank you. Questions?
Do any of the sources in your sample have Kepler or TESS light curves? Because we detect exocomets in transits in Kepler and TESS as well. Yeah, there was a paper recently published from Beta Pic of finding the transits. You have to. Mhm. Yeah, it would be interesting. Yeah.
Any further questions? Okay. Perfect. Thank you very much again.